Chesapeake Bay, Maryland, August 12, 1942, and Admiral Harold Bowen stands aboard the cruiser USS Cleveland, watching his gunners prepare to fire at 3 radio-controlled drone aircraft that are about to take off from a nearby airfield. The Navy has scheduled 2 full days of testing for a new artillery shell fuse that most officers believe cannot possibly work as advertised, a device so small it fits in the nose of a 5-inch shell, yet contains a complete radio transmitter and receiver that will supposedly detect approaching aircraft and detonate automatically when close enough to destroy the target. The Navy's Bureau of Ordnance has been skeptical about this contraption developed by civilian scientists, and they've designed these tests to prove the fuse will fail under real combat conditions, allowing them to cancel the program and redirect resources to more conventional weapons. What Admiral Bowen and the assembled officers cannot know, what even the optimistic scientists from Section T who developed this fuse barely dare to hope, is that within minutes this test will end, not because the fuse fails, but because it succeeds so spectacularly that continuing the test becomes pointless. The 3 drone aircraft take off and begin evasive maneuvers, and Cleveland's gunners open fire with shells tipped with the experimental proximity fuses, and on the very first day of what was supposed to be a 2-day test, just 4 shells destroy all 3 drones. The aircraft literally blown out of the sky by shells that exploded near them without requiring a direct hit. Admiral Bowen immediately cancels the rest of the test and orders the fuse into mass production, understanding that he has just witnessed a weapon that will change naval warfare forever. The story of the proximity fuse begins not with American innovation, but with British desperation. The Royal Air Force faces the Luftwaffe in 1940 with anti-aircraft guns that require gunners to estimate an aircraft's altitude, set a mechanical time fuse by hand, load the shell and hope the aircraft hasn't changed course or altitude by the time the shell reaches the predetermined explosion point. British scientist Samuel Curran at the Telecommunications Research Establishment understands the fundamental problem, that hitting a fast-moving aircraft with a timed explosion is like trying to shoot a bird by throwing a firecracker and hoping it explodes at exactly the right moment, requiring impossible precision from both the gunner's calculations and the fuse's timing mechanism. Curran and his colleagues William Butemont, Edward Shire, and Amos Thompson begin exploring the idea of a fuse that could sense its target and detonate automatically, considering various mechanisms including photoelectric cells that might detect the shadow of an aircraft, acoustic sensors that could hear engine noise, capacitive systems that might detect the electrical properties of a metal aircraft, and radio systems similar to radar that could bounce signals off the target and measure the return. The British team makes progress on photoelectric and capacitive designs, but they face an insurmountable problem. The vacuum tubes and circuits required for these systems are too large and too fragile to survive being fired from a gun, where the shell experiences acceleration forces of 20,000 times the force of gravity in the first few feet of its journey down the barrel. When the Tizard mission travels to the United States in September 1940, carrying Britain's most valuable military secrets including the cavity magnetron that will revolutionize radar, they also share information about their proximity fuse research with American scientists who have been working on similar problems. Admiral Harold Bowen, head of the Navy's research office, has already been thinking about proximity fuses because he understands that the Japanese threat in the Pacific centers on aircraft carriers, whose planes will attack American ships at ranges where conventional anti-aircraft fire is largely ineffective. On August 12, 1940, exactly 2 years before the successful Cleveland test, Admiral Bowen formally requests that the National Defense Research Council begin development of a rugged proximity fuse specifically designed to survive the violent acceleration of naval 5-inch guns. The job falls to Merle Tuve, a 40-year-old physicist at the Carnegie Institution's Department of Terrestrial Magnetism in Washington, D.C., a man whose previous work on radio technology and high-altitude research has given him exactly the combination of theoretical knowledge and practical engineering skill needed to solve what many consider an impossible problem. Tuve assembles a team that includes Richard Roberts, Lloyd Berkner, Lawrence Hafstad, and other physicists and engineers, forming what becomes known as the Tuve team as Section T, and they begin by studying every previous attempt to create a proximity fuse, finding, as one team member later recalls, one fairly thick book of failures and one thin book of possibilities. Section T faces challenges that would seem insurmountable to anyone unfamiliar with the demands of artillery, because the proximity fuse must accomplish things that contradict the normal rules of electronics and engineering. The device must fit inside a shell nose that measures just 5 inches in diameter and leaves room for only about 1 pint of volume after accounting for the explosive charge and the shell's structural components. The fuse must contain a complete radio system, something that in 1940 typically fills an entire room with equipment, miniaturized to fit in a space the size of a milk bottle. The electronics must survive acceleration of 20,000 g-forces when the gun fires, meaning every component experiences forces equivalent to 20,000 times its own weight trying to tear it apart in the first milliseconds after firing. The fuse must withstand the centrifugal forces created by the shell's spin, as rifled guns rotate artillery shells at up to 30,000 revolutions per minute to stabilize their flight, creating forces that want to fling every component outward from the shell's centerline. The device needs a power source that can operate in temperatures ranging from 100 degrees Fahrenheit in tropical conditions to minus 50 degrees in Arctic operations, and this battery must activate only when the gun fires to prevent gradual discharge during storage. The radio system must operate for the few seconds of the shell's flight, transmitting signals, receiving reflections from nearby objects, processing these signals to determine range, and detonating at precisely the right moment to maximize the explosive effect on the target. And all of this must be manufacturable in quantities of millions of units by companies that have never built anything like it, at a cost low enough that the Navy can afford to use these shells routinely, rather than hoarding them for special occasions. Tuve and his team approach these problems systematically, starting with the fundamental question of what type of sensing mechanism will work best. They quickly eliminate optical systems because they cannot reliably distinguish aircraft from clouds and require line of sight that might be blocked by smoke or weather. Acoustic systems fail because aircraft engines at combat ranges are too quiet to detect reliably, and the noise of the gun firing and the shell's passage through air overwhelms any acoustic sensor. Capacitive systems show promise but prove too sensitive to moisture and atmospheric conditions to be reliable. This leaves radio frequency sensing essentially a miniature radar system that can transmit a signal, receive its reflection from nearby metal objects, and use the Doppler shift in frequency caused by the relative motion between shell and target to determine when detonation will be most effective. Lloyd Berkner, working on the circuit design, makes a crucial breakthrough by separating the transmitter and receiver circuits, allowing the fuse to continuously transmit while simultaneously listening for returning signals without the transmitter overwhelming the receiver. This seemingly simple innovation solves a fundamental problem that had stopped previous attempts at radio proximity fuses, and it becomes the basis for all subsequent development. The vacuum tube problem proves the most difficult challenge, because standard radio tubes of 1940 are glass envelopes several inches long containing delicate wire filaments and internal structures that shatter instantly under the forces of gun firing. Section T initially experiments with rugged tubes designed for military radios, but these tubes literally explode when subjected to even a fraction of the acceleration forces that an artillery shell experiences. The breakthrough comes from an unexpected source when the British place an order with Western Electric and RCA for 20,000 miniature vacuum tubes designed for hearing aids, and Admiral Bowen's team correctly deduces that the British are experimenting with proximity fuses, and these tiny tubes might be rugged enough to survive gun firing. Section T obtains samples of these tubes from Raytheon and Sylvania, and begins a brutal testing program, subjecting tubes to increasingly violent impacts until they find a design that can survive. The key turns out to be a tube designated as the WE316A, produced by Western Electric for hearing aids, which is small enough to fit in the fuse, operates on low power suitable for battery operation, and has an internal structure robust enough to handle the shock of firing. But even these tubes require extensive modification, with engineers working with Sylvania to develop mounting systems that cushion the tubes, filling techniques that prevent internal structures from vibrating apart, and materials that prevent the glass envelope from shattering under pressure. James Van Allen, a young physicist who will later discover Earth's radiation belts, joined Section T in 1942 and takes responsibility for developing the miniature vacuum tubes that will make the proximity fuse practical. Van Allen works with Sylvania engineers to create tubes that are smaller, more rugged, and more reliable than anyone thought possible, developing production techniques that allow Sylvania to manufacture these specialized tubes in quantities of hundreds of thousands. Each proximity fuse requires 5 vacuum tubes, and Van Allen's tubes must operate reliably at extreme temperatures, survive not just the firing acceleration, but also the aerodynamic heating and vibration during flight, and function properly despite the electrical interference created by the shell's passage through air. The tubes he develops become miniature masterpieces of engineering, with specially reinforced internal structures cushioned mounting systems, and careful attention to every detail of their construction. And these tubes are crucial to making the proximity fuse reliable enough for combat use. By early 1942, Section T has grown to over 100 people working in the Carnegie Institution's buildings, and they're running out of space for the expanding development and testing program. TUVE approaches Johns Hopkins University in March 1942, requesting that the university sponsor a new laboratory to handle the proximity fuse program, but he cannot tell the university trustees what the laboratory will do, because everything about the fuse remains classified at the highest levels of secrecy. The trustees initially refuse, unwilling to commit university resources to an unknown project, but Vannevar Bush, head of the Office of Scientific Research and Development and former president of the Carnegie Institution, contacts President Franklin Roosevelt, who personally intervenes to convince Johns Hopkins President Isaiah Bowman to accept the project. The trustees reverse their decision, and the Applied Physics Laboratory is born, taking over a 3-story building on Georgia Avenue in Silver Spring, Maryland, that formerly housed a garage and Social Security offices. Section T becomes a PL, with TUVE as its first director, and the laboratory begins the transition from research and development to overseeing mass production of a weapon that must be manufactured in quantities that no one has ever attempted for such a complex electronic device. The battery system requires innovation equal to the vacuum tubes, because conventional batteries cannot withstand the shock of firing and will discharge over time if left active in stored ammunition. Section T develops a reserve battery that stores its components separately and only activates when the shell is fired, using the force of firing to break small glass ampoules containing electrolyte that then combines with the battery's electrodes to generate power. This design means that shells can be stored for months or years without the battery degrading, and the battery activates automatically within milliseconds of firing, providing power for the fuse's brief operating life. The safety system proves equally important, because the fuse must not arm until the shell has travelled far enough from the gun to prevent premature detonation that might destroy the firing ship. Engineers develop a mechanical safety that uses the centrifugal force from the shell's rotation to move a firing pin into position, with the safety designed so that it requires several seconds of high-speed rotation before the fuse becomes active, ensuring that the shell is well away from the ship before it can detonate. Gunners are understandably nervous about firing shells with sensitive radio equipment and high explosives, and Section T must convince them that the safety systems are reliable, eventually demonstrating by dropping armed fuses from buildings and hitting them with hammers to prove they will not detonate accidentally. By June 1942, Section T has a working fuse designated as the Mark 32, designed specifically for the Navy's 5-inch 38 caliber gun, the primary anti-aircraft weapon on American cruisers and destroyers. The fuse measures about 5 inches long and 2 inches in diameter at its widest point, weighs approximately 1.5 pounds, and contains 130 separate components including 5 vacuum tubes, a battery, a radio transmitter operating at about 180 MHz, a receiver sensitive enough to detect reflections from aircraft at useful ranges, signal processing circuits that determine when to fire, a detonator, and various safety and arming mechanisms. The entire assembly must be manufactured to tolerances that seem impossible for mass production, because tiny variations in component placement or circuit values can make the fuse unreliable or completely non-functional. Section T must solve not just the technical problem of making one fuse work, but the manufacturing problem of making millions of fuses that all work identically, and this requires developing entirely new production techniques, including some of the first applications of printed circuit boards, where electrical connections are etched onto insulating boards rather than hand-wired. The August 1942 test aboard Cleveland validates the fuse concept so dramatically that the Navy immediately begins the largest industrial mobilization around a single weapon component since the start of the war. Crosley Corporation, known for manufacturing radios and household appliances, converts its Cincinnati factories to produce proximity fuses, eventually building about 25% of all fuses manufactured during the war using a workforce of 10,000 people. RCA, Eastman Kodak, General Electric, Sylvania, and dozens of other companies receive contracts to manufacture fuses or their components, with more than 100 companies eventually involved in the program. The cost is staggering, with procurement contracts increasing from $60 million in 1942 to $200 million in 1943, $300 million in 1944, 1944, and topping $450 million in 1945, for a total of over $1 billion, equivalent to more than $14 billion in modern currency. The price per fuse drops as production volume increases and manufacturing techniques improve, falling from $732 per fuse in 1942 to just $18 in 1945, making the proximity fuse one of the most successful examples of wartime mass production. By the end of the war, American industry produces over 22 million proximity fuses, a manufacturing achievement comparable to building 22 million miniature radar sets. The first combat use of the proximity fuse occurs on January 5, 1943, when the cruiser USS Helena operating off Guadalcanal comes under attack from 4 Japanese Ichi-D-3A dive bombers, obsolete aircraft that nevertheless remain dangerous because of their accuracy and their pilots' willingness to press attacks to point-blank range. Helena's anti-aircraft gunners fire conventional shells at the approaching aircraft, then switch to proximity-fused ammunition as the Japanese planes break off their attack after one scores a hit on the nearby New Zealand cruiser Achilles. 2 5-inch salvos, probably 5 to 10 shells total, destroy one of the retreating dive bombers, even though none of the shells directly hit the aircraft. The bomber simply disintegrates in mid-air as proximity-fused shells explode near enough to tear it apart with shrapnel, demonstrating exactly what Section T intended, that near misses can become kills if the miss is close enough and the explosion occurs at the right moment. Naval historian Samuel Eliot Morrison, documenting this action, notes that the attackers did not escape with whole hides and describes the proximity-fused Mark 32 shell having one of its first combat tests, understanding that he is witnessing the beginning of a revolution in anti-aircraft warfare. The effectiveness of the proximity fuse becomes statistically undeniable during 1943 as more ships receive the new ammunition and combat data accumulates. Pacific theater analysis shows that the proximity fuse is 3 to 4 times more effective than conventional time fuses, meaning 3/4 fewer shells are needed to achieve the same number of kills. Night engagements show even more dramatic improvements, with kill ratios increasing by 370% because proximity fuses work equally well regardless of visibility, while time fuses require visual observation to calculate the proper setting. During 1943, naval guns fire 36,370 anti-aircraft rounds in combat, and although only 25% of these rounds use proximity fuses, these account for 51% of all aircraft destroyed by naval gunfire. The proximity fuse increases the lethal fragment area of a 5-inch shell from about 60 square feet for a time-fused shell to over 3,000 square feet, a 50-fold increase that means the shell does not need to explode nearly as close to the target to achieve a kill. Admiral R. Lee Burke, who serves as Chief of Staff to Admiral Mark Mitcher, commanding the Fast Carrier Task Forces, later states that without proximity fuses, ship losses and casualties in the Pacific would have been enormously larger, and that proximity-fused ammunition knocked down enemy planes by dozens. The Pentagon's fear about the proximity fuse, the nightmare that keeps security officers awake at night, is that a dud shell might fall on land where Japanese or German forces could recover it, reverse engineer the design, and develop their own proximity fuses, or devise countermeasures that would render the American fuse ineffective. This fear means that through most of 1943 and 1944, the proximity fuse can only be used over water, where dud shells sink to the ocean bottom beyond enemy recovery, and the Navy broadcasts spurious radio signals during combat to mask the distinctive frequency signature of proximity-fused shells, hoping to prevent Japanese listening posts from even detecting that something new is being used. The Germans and Japanese both developed their own proximity fuse programs, with Germany pursuing more than 30 different designs, including acoustic fuses triggered by engine noise, electrostatic fuses that detect the electrical properties of aircraft, and radio fuses similar to the American design. But none of these programs succeed in producing a fuse rugged enough to survive gunfiring and reliable enough for combat use. The technical challenges that Section T spent 2 years solving prove equally insurmountable for Axis engineers working under the pressure of a losing war with dwindling resources and increasing Allied bombing of their research facilities. The first use of proximity fuses over land comes in June 1944, when Germany begins launching V-1 flying bombs against London, cruise missiles that terrorize British civilians and threaten to disrupt preparations for the Normandy invasion. British anti-aircraft guns initially shoot down only about 17% of the V-1s that reach the coastal gun belt, a rate that allows hundreds of missiles to get through to strike London each day. Winston Churchill personally requests proximity fuses from the United States, and on June 12, 1944, American proximity-fused ammunition begins arriving at British anti-aircraft positions. The effect is immediate and dramatic, as the kill rate against V1s climbs to 79% by the end of August, reaching 82% during the best single day. One British anti-aircraft unit equipped with proximity fuses destroys 48 of the first 75 V1s they engage, a success rate that effectively defeats the V1 threat and allows London to survive the bombardment. British authorities later credit the proximity fuse with saving thousands of civilian lives, turning what could have been a catastrophic terror campaign into a manageable problem that British defences can handle. The success against V1s demonstrates that the proximity fuse works not just against manoeuvring aircraft, but also against small, fast-moving targets that are difficult to hit with conventional fuses. December 16, 1944, and the German army launches its last major offensive in the west. Attacking through the Ardennes forest in what becomes known as the Battle of the Bulge, an American artillery units suddenly have authorization to use proximity fuses over land for the first time in the European theatre. Colonel George Axelson, commanding the 406th Artillery Group supporting cavalry troops being overrun by German forces near Monschau, makes the decision to use the new fuses 3 days before General Eisenhower officially lifts all restrictions, understanding that the emergency justifies breaking the embargo. The effect on German infantry caught in the open is devastating as artillery shells explode 30 to 50 feet above ground, showering troops with shrapnel that conventional ground-burst shells would bury harmlessly in the dirt. German commanders have felt safe from artillery fire during bad weather because they believe accurate fire requires visual observation that fog and clouds prevent, but proximity fuses need no observation, detonating automatically at the optimal height regardless of visibility. General George Patton writes to the War Department describing how proximity-fused shells caught a German battalion trying to cross the Sauer River and killed 702 soldiers by actual count, and he states that the new shell with the funny fuse is devastating and that its use requires a revision of the tactics of land warfare. German prisoners repeatedly speak of the demoralizing effect of artillery that explodes above their positions with no warning, and German intelligence offers rewards for any soldier who can recover an intact proximity fuse for examination. By late December 1944, all restrictions on proximity fuse use are lifted, and American artillery in Europe fires 200,000 proximity-fused shells during the Battle of the Bulge and the subsequent advance into Germany. The psychological impact on German forces proves as significant as the physical casualties, as soldiers become unwilling to leave their bunkers during artillery barrages, knowing that overhead bursts can reach them anywhere. The proximity fuse changes ground warfare tactics fundamentally, making it possible to destroy targets on the reverse slopes of hills where conventional artillery cannot reach, to clear minefields by exploding shells above the mines, to cut communication wires more effectively, and to create overwhelming casualties against infantry in the open. German soldiers who survive proximity-fused barrages describe the horror of shells that explode overhead without warning, creating inescapable patterns of shrapnel that turn open ground into killing zones. Reichsmarshal Hermann Göring, interrogated by American officers after the war, admits that Germany was working on proximity fuses and estimates they would have achieved production capability in 3 or 4 months, but acknowledges that German forces never developed an effective counter to the American weapon. The Pacific War sees even more dramatic use of proximity fuses as American naval forces fight their way across the Central Pacific toward Japan against increasingly desperate Japanese air attacks. The kamikaze threat that emerges in late 1944 makes proximity fuses even more valuable, because suicide attacks give pilots motivation to press through defensive fire that might deter conventional attackers, and stopping kamikazes requires destroying the aircraft before they reach the ships. Between October 1944 and January 1945, American anti-aircraft guns fire 400,000 rounds at attacking aircraft. An analysis shows that proximity-fused ammunition requires an average of 250 rounds per kill against kamikazes, while time-fused ammunition requires over 900 rounds per kill, a nearly 4-to-1 advantage that translates directly into saved ships and sailors. During one particularly intense action in May 1945, the destroyers USS Hadley and USS Evans, supported by gunboats and fighter aircraft, face attacks by 156 Japanese aircraft over the course of several hours. The ship's 5-inch guns, firing proximity-fused ammunition, account for 35 confirmed kills, with Hadley downing a dozen aircraft and Evans destroying 23 before taking 4 kamikaze hits that force her retirement. The battle demonstrates that properly used proximity fuses can allow even small ships to survive massive air attacks that would have been overwhelming with conventional ammunition. Secretary of the Navy James Forrestal states after the war that the proximity fuse helped blaze the trail to Japan, and that without the protection this ingenious device gave surface ships, the westward advance across the Pacific could not have been so swift, and the cost in men and ships would have been immeasurably greater. Vannevar Bush, who oversaw the entire Office of Scientific Research and Development, including the Proximity Fuse program, credits the fuse with 3 significant effects that changed the war's outcome: defending Britain against V-1 attacks, protecting the Pacific Fleet from Japanese air attack, including kamikazes, and revolutionizing artillery effectiveness in ground combat. Bush estimates that the proximity fuse increased the effectiveness of 5-inch anti-aircraft guns by a factor of 7, making each gun as effective as 7 guns firing conventional ammunition. And this multiplier effect means that the proximity fuse effectively created thousands of additional anti-aircraft guns, without requiring any additional manufacturing capacity, crews, or training. The billion-dollar investment in proximity fuse development and production proves to be one of the most cost-effective weapons programs of the entire war, saving far more in prevented ship losses and reduced casualties than it costs to develop and manufacture. The proximity fuse remains highly classified until after Japan surrenders, with the full details of its operation not released until the 1950s. And even after the war ends, American intelligence carefully tracks all captured proximity fuses to ensure none fall into unauthorized hands. The Germans and Japanese captured some dud proximity fuses during the war, including several recovered after the Battle of the Bulge, but analysis shows they were unable to duplicate the design, partly because the miniature vacuum tubes required manufacturing techniques and materials they did not possess, and partly because the integrated nature of the fuse meant that understanding one component did not reveal how the entire system worked. American fears that the Germans might develop countermeasures prove unfounded, as German electronics industry simply lacks the capacity to create the precision components needed for a working proximity fuse, and the deteriorating war situation prevents them from devoting resources to a crash development program. The secrecy surrounding the proximity fuse proves so effective that most American servicemen who fire proximity-fused ammunition have no idea how it works, knowing only that the shells marked with special codes are more effective than conventional rounds. The technological innovations developed for the proximity fuse have effects far beyond their immediate military application, as the techniques for miniaturizing electronics, mass-producing precision devices, and creating rugged electronic components lay groundwork for the entire post-war electronics industry. The printed circuit boards developed to manufacture proximity fuses become standard in all electronics manufacturing. The vacuum tube production techniques lead to improvements in radio and television manufacture, and the system engineering approach used to integrate multiple technologies into a working weapon becomes a model for complex development programs throughout the Cold War. James Van Allen's work on miniature rugged vacuum tubes directly influences his post-war research on space instrumentation, leading to the instruments aboard Explorer 1 that discover Earth's radiation belts. The Applied Physics Laboratory continues as a major defense research institution, expanding from its proximity fuse origins to work on guided missiles, satellite systems, and other national security projects. The collaborative model that Section T pioneered, bringing together university researchers, industrial manufacturers, and military operators to solve complex problems, becomes the template for American weapons development throughout the Cold War and beyond. Military analysts comparing the proximity fuse to other World War II innovations place it alongside radar and the atomic bomb as the 3 developments that most influenced the war's outcome, and some argue that the proximity fuse had greater overall impact because it was used far more widely and saved more lives than either of the other technologies. Air Force General Sam Phillips states in a 1988 interview that if the Germans had perfected an effective proximity fuse before the war ended, the outcome could have been significantly affected, acknowledging that American and British bombers would have faced losses that might have made the strategic bombing campaign unsustainable. The proximity fuse demonstrates that technological superiority can multiply combat effectiveness far beyond what additional manpower or conventional weapons could achieve, that small teams of innovative engineers and scientists can create weapons that change the strategic balance, and that the industrial capacity to manufacture complex weapons in massive quantities becomes as important as the original invention. The $1 billion spent on proximity fuses represents less than 1% of America's total war spending, but arguably contributed more to victory than many weapons programs that cost far more. The veterans of Section T and the Applied Physics Laboratory carry with them the knowledge that they created something that saved thousands of lives, both by destroying enemy aircraft before they could attack ships and by ending the war sooner through more effective weapons. Elmore Chatham, a radio engineer who worked on the proximity fuse at APL, recalls decades later that the team knew they were working on something important, but could not fully appreciate its impact until after the war, when casualty statistics and operational reports revealed how many ships survived attacks, how many sailors came home because shells could explode in the right place at the right time without requiring impossible precision from gunners. The engineers who solved the problem of fitting a radio into a shell, who developed tubes that could survive 20,000 G-forces, who created batteries that activated automatically, who designed safety systems that prevented accidents. These men and women working in offices in Silver Spring and factories in Cincinnati and testing grounds in Virginia created a weapon that turned anti-aircraft guns into guided weapons decades before the concept of precision-guided munitions became standard military doctrine. The proximity fuse represents American innovation at its finest, born from the collaboration between civilian scientists, military officers willing up to support unconventional ideas, and an industrial base capable of manufacturing millions of complex devices to exacting standards. In the final analysis, the proximity fuse stands as perhaps the most successful weapons development program of World War II when measured by return on investment, speed of development, reliability in service, and impact on combat outcomes. From Merle Tuve's first experiments at the Carnegie Institution in August 1940 to the first combat success aboard USS Helena in January 1943, just 29 months elapsed, an astonishingly short development time for a revolutionary weapon. The fuse achieved operational reliability exceeding 90% by 1944, meaning that 9 out of 10 shells performed exactly as designed under the most demanding combat conditions. The production of 22 million fuses represents an industrial achievement that demonstrates American manufacturing capability at its peak, coordinating over 100 companies to build components that must work together perfectly in a system where failure means the difference between life and death. The proximity fuse saved London from the V-1 onslaught, protected the Pacific Fleet from kamikaze attacks, and revolutionized artillery effectiveness in ground combat, 3 distinct and decisive contributions to Allied victory. The story of America's proximity fuse is ultimately one of scientific ingenuity, engineering excellence, and industrial might combined to create a weapon that turned the theoretical concept of a smart shell into a practical device that gunners could fire by the thousands, knowing that each shell carried within it the intelligence to find its target and detonate at exactly the right moment, transforming anti-aircraft guns from weapons that scattered shells randomly in the sky, hoping for lucky hits, into precision instruments that destroyed enemy aircraft with mechanical certainty.